Welcome to the R session that supplements the lecture on modeling skills. In this session, we will work through two examples. In the first example, we will take up the CO2 data set that we briefly looked at in the data analysis session. Once again, we start with a clean slate from R and load the CO2 data set that comes with the base package. Always remember, this CO2 data set need not be just with one package. There are other packages when you load. You can also have the same data set. I am referring to the CO2 data set that comes with the base package called data sets. So, it has loaded the CO2 data, and to confirm that is indeed the same data that we worked with last time, just look at the plot and you must quickly notice that it is indeed the same one. It has a linear trend, at least prima facie, but it could be a quadratic trend or a cubic one, you do not know. But definitely it has a trend, it's a function of time. On top of it, we also have an oscillatory trend which we would like to model, and then there could be a stochastic component to it which also has to be modeled. So, the goal here is to model this series so that I can use that model for forecasting the CO2 levels. We shall not go through the complete modeling exercise, because a complete modeling exercise may also call for some theory of random processes where we learn how to model the stochastic components. I will only show you how to model the trend and the oscillatory part, and then the rest is reserved for some other course, or maybe if you are already familiar with it, you can go ahead and do it. So, here the first thing that we would do is we would model the trend, where the trend is a function of time. So, the time is a regressor and the CO2 is the variable of interest. Or to extract the time vector, we could use the time command. As you must notice here in the workspace panel, CO2 is a time series object, and therefore, it is always going to have timestamps as one of the attributes. We extract the timestamps and collect them in the tvec. It is just a variable name that I have chosen. Now, we could extract the trend using what a routine known as LM in R. LM stands for linear modeling or linear models. The estimation algorithm underneath this routine is a least square, standard least squares algorithm with a lot of other features as well. You could, for example, model only using a subset of data, you could supply weights and so on, but we are going to use the most plain or vanilla version of LM, and let us call this model as lin CO2. That is just a variable name that I am choosing, and let me show you what I am doing here. So, I say here I supply the formula that I want. Now, by formula what we mean is the symbolic relationship between the predicted variable, which is CO2, and the regressor, which is tvec. I do not have to tell LM that there is an intercept term as well. So, it is understood implicitly that there is an intercept term. On the other hand, if I do not want the intercept term, for some reason I believe there is no intercept term, then I could use this syntax. But at the moment we do not know if there is an intercept or not. Of course, we can look at things visually, but let us rely on the algorithm first to tell us if there is an intercept. So, this is the model now we have. Now, we can examine this model, and we should do it to proceed further. The summary command is a very multi-purpose command which applies to different types of objects. Lin CO2 is an LM type object, basically it is a model type object, and it has several components to it. But first let us look at the summary and see what it prints out. So, on the top it gives you the formula, which essentially is a symbolic relationship that we are modeling, and then it gives you some statistics on residuals, what is a median and so on, gives you some idea of whether the residuals are of 0 mean, what is the range and so on, but we will come back to that. the primary interest for us is the estimates of the intercept and the slope. We have just fit a linear model. And as you can see here, there are 4 columns under the coefficients heading. The first column gives us the estimates, the second column gives us the standard error, as we call 1 sigma error or the average error in the respective estimates, and then the last 2 pertain to the statistics on these estimates, and there are also stars here. So, let us quickly understand what all of this is about. So, the estimates, of course, we can read off. By themselves, the estimates do not carry a lot of information. They have to be interpreted in the context of the standard error. So, for what I mean by that is, suppose the estimate here was a very small value, you cannot come to the conclusion that the estimate can be neglected. Suppose the slope turned out to be 10 power minus 4, it has certain units. So, it is going to be sensitive to the unit. So, the value of something of the order of 10 power minus 4 by itself does not make any meaning or carry any significant meaning to it, unless it is interpreted in the context of the standard error. So, the standard error here is much smaller relative to the estimates themselves, conveying the fact that these estimates are to be treated as significant, which means you cannot really treat them to be negligible or theoretically 0. Now, the t value column is something that I will not go over. It's pertaining to hypothesis testing. So, maybe in the course on hypothesis testing, you will find a lot of details on this. The last column reports what is known as the p value, and the p value is again the probability of estimating this parameter or obtaining an estimate larger than what we have observed. But without going too much into the details, a simple interpretation is, if the p value is extremely low, then the null hypothesis that the parameters are truly 0 valued. What are the parameters here? The intercept and slope, and that the entire purpose of this analysis is to test the hypothesis that the individual parameters are truly 0. So, when the p value is extremely low, the null hypothesis that the parameters should be are 0 valued must be rejected. And if you recall, we use the phrase, if the p value is low, the null hypothesis must go. So, it is just a catchy phrase to remember, and the 3 stars here are kind of telling you that the parameter estimates are significant. They're all same, telling you the same thing. You can look at it from a hypothesis testing viewpoint, or you can look at it from a significance test for the parameters. Either way, what it is trying to tell us is, we cannot ignore the parameter estimates practically. Therefore, this linear model should have both slope and intercept. Now, the question is, if this linear model is sufficient. We have discovered that this linear model has significant parameters in it. Now, to do that, we can look at the residuals. For example, we could plot the residuals. The nice thing about RStudio is it tells you whether the field that I am typing is a valid field in the LinCO2 model, and by default it may plot a scatter plot. So, we will plot a line plot. So, you can see here the linear trend has been taken off, but there seems to be some quadratic trend as well, because a pure sine wave cannot of that frequency cannot have a shape like that. So, maybe we can fit a quadratic model as well and check if the residuals are much better behaved and so on. So, to build a quadratic model, you can go through this syntax here, and this is something that you may want to pay closer attention to. Again, the same story, we use LM, specify the relationship between the predicted variable and the regressor. The regressor is, as usual, our time vector. This time around we want to build a quadratic model. So, our model is y is some a naught plus a1t plus a2t square. A naught is implicitly understood to be present. So, we are supplying t vec here in the formula, forcing LM to fit an a1, and then we use this syntax I of t vec square. This essentially tells R that t vec square is another regressor. if we do not do this and instead we say T vec plus T vec square, what R would do is it would add up T vec plus T vec square and treat that as a single regressor, and that is not what we want, all right. So, always remember, when you are creating regressors out of a single explanatory variable, here the time vector, then we should follow this syntax. Tomorrow you may have T vec plus maybe cubic term or a logarithm term, something like that. All of that has to be, each regressor has to be encased in a similar in a fashion like this, all right. So, we have a model, and now we can once again look at the quadratic model and look at the parameter estimates. Of course, technically speaking, we should look at the residuals first and then the parameter estimates, but we are taking a slight deviation from that. So, again here the stars for me indicate, or the p values as well indicate, that the parameter estimates are significant. That is, we can reject the null hypothesis that each of the terms in my model, a naught intercept, a1 the first coefficient corresponding to t, a2 the second coefficient corresponding to t square, all not 0, or the estimates themselves are significant. We do not have, unfortunately in this case, a true model. I do not know, or we do not know how this CO2 was generated. The actual process is far more complicated perhaps than the model that we are trying to fit, remember that. So, there is no truth to compare, and that is why we go through this hypothesis testing. Of course, if you know the truth, then all this modeling exercise is futile, all right. So, there are a bunch of other pieces of information here that are reported by summary, but to go over that requires a good set of lectures on linear regression, and therefore, I am avoiding that. But if you are already familiar, you will enjoy these pieces of information and make more meaning out of this analysis. So, once again let us look at the residuals and see if this time the trend, the quadratic trend has vanished, right. So, this time we look at the residuals, yeah, the trend has vanished, all right. There could be of course a cubic one, we could do that and then go on and check if there was a fourth order polynomial trend and so on. I leave that to you now that I have shown you how to do this. Let me move on to the next step where we analyze the residuals. For now, we shall assume that the quadratic trend is the only trend, but you should not do that, go further and fit a cubic trend. We will assume that the quadratic trend is only one and analyze the residuals. Now, when we look at these residuals here, we can clearly see an oscillatory behavior, which means we can now try to extract the frequency of this oscillation. That means, the CO2 level has a periodicity to it, it repeats itself after a certain time. Now, how do we extract the frequency? I can do this visually, but that is going to be too rudimentary an analysis. Let us instead use the Fourier transform route. I do not know how many of you are familiar, but if you are not, then Fourier transforms allow us to detect the periodicity in a simple way by constructing what is known as a power spectrum or a power spectral density, where you analyze the contributions of different frequency components within the signal to the total power of the signal. And the simple rule of thumb, which has a theoretical basis to it, is in a power spectral plot, if I see a peak at a certain frequency, then that frequency component is significantly present in the signal. Now, the base package in R does come with tools to perform spectral analysis or Fourier analysis. There is a command called spectrum, but I prefer the time series analysis package, and it is called the TSA, and I am going to load that because it has a nicely wrapped routine which is built on the base package to do the spectral analysis for me. So, I have loaded the TSA package, and you should be you should see this kind of a display. Now, when I load a new package in R, always there is a possibility that some of the routines in the new package share the same name with the routines in the existing or the base package, and R gives you a warning that the following objects are now marked from but this package and so on. So, basically they are telling you that ACF, ARIMA, TAR and so on, if they are of interest to you, there is an overlapping between these two packages. So, if you have to be careful and so on, but anyway we will not go into that. But one thing that I want to tell you, the TSA package also has a CO2 data set which looks quite a bit different from the CO2 package data that we have been working with. Anyway, so let us quickly look at the periodogram. The command is periodogram, and I am going to really directly pull the residuals here, periodogram of quad CO2 dollar residuals. You can see the dollar operator is being used to extract the component, and beautifully it shows me the frequency content of the signal. So, the way to interpret this plot here is, on the x axis I have power, and on the on the y axis I have power, and on the x axis I have frequency. And what it is basically telling me is that at this frequency roughly I have the maximum power, and this obviously this you do not need to guess, is the main frequency component that we are interested in. But there is something else also the spectral analysis reveals, which is the presence of a harmonic, all right. And this is perhaps, well, to confirm whether there is a harmonic or not, harmonics are integer multiples of fundamentals. So, if you think of this big one, the frequency at which there is a big peak as a fundamental, then approximately the tinier one to the right of that can be thought of as a harmonic. And typically presence of harmonics means some kind of non-linearities in the generating phenomenon and so on. But it is very interesting because visually we could not see this peak. So, you see mathematical analysis brings out what we cannot really visually see, but at the same time visual examination is very important. Now, if you look at the power contributions from very low frequencies, almost near 0 frequencies, there seems to be some significant contribution that is perhaps indicative of a very low frequency trend, which probably is indicating that we should have also modeled the cubic one. Even our visual analysis in fact revealed that. So, if you go back to the plot, there seems to be some kind of a cubic trend. In fact, if you plot the cubic one, I should tell you that you will find the A3, that is the third coefficient, the fourth coefficient also being significant. So, try it out, try fitting the cubic one and the fourth order one and see what the analysis tells you, whether the trend is indeed a third order or a fourth order polynomial. And then we have already learned how to analyze the residuals, extract. So, now you use these models to remove the trend and the sinusoid, and then you can see the residuals, which of course I will not go through at this moment, but you can always write to us if you want to know how to do it in more detail. We can send you the script. All right then, so let us move on to the second example. In the first example, we have learned essentially how to perform linear regression in a systematic manner in R. We are also going to do one more linear regression here, but this example pertains to that of overfitting example that we went through in the lecture. So, let us clear the screen here and generate the data required for the overfitting example. What I am going to do is I am going to generate the input as a sequence here from 0 to 4 in steps of 0.02. So, I have 201 values of UK, and correspondingly I will generate the noise free response. If you recall, go and refer to the slide which gives you the relationship or the data generating expression for the noise free part, and this is what we had, and let us call that as xk. Now, as we have always said, we never get access to the true response, we only have access to the measured value of it. So, to make the situation realistic, now we add noise, and we add noise in this fashion, right. We add Gaussian distributed noise of the same length as xk, and we also adjust the amplitude of the noise such that the signal to noise ratio is fairly high, and that is what I am doing here. by default, if I do not have the scaling factor there, the variance of Vk would be 1. It is a unit variance random noise that I would be generating. So, let us generate the measurement. Here I have Yk equals Xk plus Vk, and that is the noise part I have, noise or the measured value. So, let us simply plot here Uk and Yk and see if this is what indeed we wanted. Yeah. So, it looks pretty similar to what we wanted. Of course, it looks a bit noisy, not so noisy. You can add, if you want, you can increase the levels of noise and repeat whatever we are going to do. Now, let me go through 2 or 3 different models and then we will conclude the session. So, the first model I just want to show you, if you had access to the noise free part and you knew that the relationship is a third order polynomial, then you can let us do that here. Okay, let us call this as mod xu and call the LM and supply the symbolic relationship. So, we have here xk tilde uk plus I uk square plus I of uk cube, right. So, that is it. All right. So, that brings up the summary for the model that we just fit between x and u, and I quickly want to draw your attention to the warning message at the bottom of this display. It says that essentially a perfect fit. It has to be. So, what it says is the relationship is perfect, there is nothing left unexplained, there is no residual from this model, so to speak, and that is also reflected in the median of the residuals. They are extremely small, they are 0 up to the numerical precision. And also the parameter estimates have been identified in a perfect manner and so on, but this is all a utopian world, we do not have access to the noise free part. So, we move now to reality. I am just showing you that if you had everything in hand, the LM will perfectly identify that for you. So, let us move on to the overfitting demonstration of the overfitting example. In the lecture, I pointed out that when we overfit, that is in this example, if I fit a 4th order polynomial or a 5th order polynomial, I am overfitting. If I fit a 2nd order or a 1st order, I am underfitting. So, in practice, do we know what is the order of the polynomial? No, we do not. So, how do we go about determining it? Let us assume that we are given there is a polynomial relationship, even if we are not given, the plot of y versus u tells me or strongly indicates a polynomial kind of relationship. Now, I start guessing, we necessarily obviously rule out the first order, that is a linear one. We can begin with the 2nd order, 3rd order, 4th and 5th, but I will skip the 2nd because the primary purpose is to show overfitting, not underfitting. I will first identify the cubic polynomial relationship between y and u and then build the other 2 models. And so, let me do that here, mod yu3, sorry. So, I have here, and also what I am going to do is I am going to pick the first 150 points for building the model and use the remaining 51 for prediction. This is something that is probably going to be useful for you, and that exercise is also necessary, as I have mentioned in the lecture, for cross validation. So, in LM I can exercise this option by saying subset, use the first 150 points, you can use any 150 points or even change the length and so on. Okay. So, I have this mod UI3, let us also build the other models, right, here in a similar fashion, and the 5th order polynomial as well. So, I am going to build all of them at once. So, these are the 3 different polynomial models. Now, we want to ask how good these models are, right. A good test for these models, of course, is to look at the individual model, the parameter estimates in these individual models. So, here is a summary of the 3rd order polynomial fit, and you can see that the parameter estimates are close to the truth. In this case, I know the truth because I have simulated the data, and the estimates are quite close to their true values. You can never expect them to be exactly equal for obvious reasons, and the stars here also indicate along which are coming out of the low p values that the estimates are significant. Good. So, third order polynomial is good. We can also look at in a similar way the fourth order. Now, you see something different. I have overfit because this is the fourth order polynomial. Look at what has happened. The intercept term is pretty close to the truth, and then starts the jumble tumble here, that we have the estimates deviating from the truth significantly to the extent that the coefficient on the third order term is not significant. You can look at the error. The error in the estimate of the coefficient for u cube is quite significant compared to the estimate itself, and likewise for the fourth order coefficient as well. And that is why there are no stars here, telling you that the null hypothesis that the coefficients on u cube and u to the power 4 are 0, but we know that is partially correct, but at least we know for sure the coefficient on u to the 4 should be 0. What we should take home from this simple exercise is, when we overfit, we can have a situation where the parameter estimates, even though the true parameters are not 0, can turn out to be insignificant. So, we do not know how this overfitting is going to hurt, and I always like to give this example that data is the food for identification and parameters are guests. So, when you do not have enough food for your guests, then some guests may go satisfied and some others may go hungry. We do not know who will go hungry and who will go satisfied, but the bottom line is there will always be some guests who will go hungry, and the guests here are parameters. What we mean by hungry is here large errors. We do not want that. When we invite guests, we want all guests to actually go satisfied. So, always remember, data is food for identification. We do not want to over invite. We may under invite, but that is also not good in modeling. We want to invite exactly the number of guests that are meant for the food, because we do not want any wastage of food either, remember. And that analogy hopefully will stay with you whenever you are modeling. And we should expect a similar behavior for the other one as well. So, for the fifth order polynomial as well, you can see none of the parameter estimates except the intercept term are significant, which means they have large errors in them. So, this has obviously gone for a full toss. We can compare, I will just compare the predictions, I will show you how to compute the predictions of the models, and we can quickly compare the predictions of the third order and the fifth order polynomial on the remaining 51 points, or we can choose the full data set. We will just choose the remaining 51 points. Let me do that. So, we call this as yk hat, and okay. So, let me first, the procedure to compute the prediction is to first create a data frame. Remember that R accepts data frames for modeling and predictions and so on. So, let us create a data frame where, sorry, I can just simply say here UK 51 to 151 to 201. So, those are my that is my test data UK, and now I can make the prediction here. All right. So, mod uy3 dot test data predict dot lm, or simply predict knows by looking at the object that you feed, which is mod uy3, that is a model. It understands that it has to work on a linear model object. So, predict dot lm explicitly is telling R that the object or the model that I am supplying is a linear model type, and then I am supplying the test data on which it has to compute predictions. So, I have done that, and similarly let us do this for the fifth order as well. I leave it to you to compare the fourth order, something to work on, right, for yourself. Okay. So, we call this as yk hat. Hat is typically used in estimation for prediction, approximation and so on, and that we use the same convention. Now, let us compare the predictions here. So, I have plot, let us plot the yk first. In fact, we let us call also yk test, create a variable which corresponds to the yk for the test data. All right. So, now plot uk test or yk and test and sorry, there is no uk test, we have not created, sorry, right. So, here is the plot for the 151 to 201 points between yk and uk. This is the true the measurements. Let us ask what are the predictions of the third order and fifth order polynomial models. We can use here lines and can say uk test yk yk hat 3, and we can use a red color to see how the plot is. Sorry, okay, perhaps I can just use this, make this. Oh, sorry, this is a color. Boy, okay. So let us take a different approach here. Let us plot simply the yk hat. Right. yk test, and then plot yk hat 3. So, we can compare the predictions here. I plotted yk as a function of time, but we might as well plot as we did earlier here. We can plot it as a function of u as well. Okay, and then here lines. All right, great. And then we can also plot the maybe on blue, in color blue, the prediction from the fifth order polynomial and see where it has gone. So, you can see that in this case the predictions of the fifth order has gone apart. In the lecture we have seen that the predictions had gone unstable as well. Now, how these predictions behave completely depend on the realization of the noise that we add, but the fact is, first of all, the parameter estimates are not reliable in the fifth order case, and therefore, we should not even trust the model. Even if you were to trust that, the predictions are not so great. I can tell you, if you were to repeat this exercise, these plots here will look different and the estimates will look different, because you will generate a different realization of noise. But the bottom line is, if you were to overfit, there are two symptoms that will be clearly visible. One, that you would see the large errors in parameter estimates, which means you have overestimated, you have over parameterized your model, and two, that the predictions will fail somewhere between miserably to not so miserably, but they will be poor on a fresh data set. Always in modeling, therefore, if wherever possible have a cross validation data set. Of course, sometimes you may have too small a data, but it should always be a practice to have a test data set where you can test the trained model on the test data, pretty much like we test students trained on assignments on exam papers, right. So, go through this exercise by yourself and get a feel of what it means to model. I just also want to show you whether it is a LinCO2 or the models that we have been fitting, for example, mod yk3, sorry, uy3. If you just type, this is what it would give you, but if you want the full list of components in mod ui3, Attributes will tell you what are all the other things that are contained in each of these models that are returned by LM. You have coefficients, the fitted values, you can compare the fits. The fitted values are the predictions of the model on the training data. You can extract the residuals like we did. Then you can also get other details as to how it was called and so on, depending on how well versed you are with linear regression. There is also non-linear version of the LM routine, and there is a generalized version called GLM. The non-linear version would use the nonlinear least squares method. Hopefully someday we will have a chance to go over those as well, but we will have to conclude, and let me do that by saying by hoping that you have enjoyed this modeling session, and write back to us as always with any questions that you may have pertaining to modeling or how to fit models in R, and we will definitely be glad to help you. Have a good day.